Hi everyone, I'm Ben Sachs. My company, Sachs & Associates, does training in C and C++ for companies all over the world. So if you're interested in learning more, you can find out about us at our website, or feel free to connect with me on LinkedIn or email me questions, things like that. So I'm going to be talking today about this concept of freestanding C++, what it is, where it comes from, where it might be going, and what you can do in the meantime before it gets to that place where it might eventually be going. And the story of freestanding C and C++ kind of starts in the same place as the whole standardization process for C and C++ in general. So the question that we don't often ask ourselves this, but why do we have language standards? What's the point of standardizing C and C++? It's the sort of thing that we just sort of take for granted a lot of the time, but it's worth taking the time every so often to step back and think about that a little bit. And there are lots of different reasons that we might want to standardize C++, but one of the big benefits, I think, is portability. And portability comes in a couple of different flavors. The one we usually talk about is that having a language that's portable means that we can write programs that are portable. So we can write a single program using one code base and compile it with several different tool chains targeting many different platforms and have a reasonable expectation that the program that we get out the other end will actually run and do the right thing. But having a portable language also means that your skills are portable. The things that you learn in the process of writing your first C or C++ program can then be applied to writing more C and C++ programs, even if those other programs are targeting completely different environments using completely different tool chains. So portability is important, but making C and C++ portable is hard because, well, for lots of reasons, but one of the reasons that making C and C++ portable is hard is that they're used to write so many different kinds of applications. Not just traditional desktop and server applications, but things like operating systems or embedded systems, some of which use an operating system and some of which don't, some of which run on bare metal. And so when you're writing programs like operating systems and embedded systems, you're often operating in environments that often have some quite severe limitations. And those limitations affect your ability to use certain parts of the language in the library. So for example, you might not have a file system available. If you're implementing an operating system, usually the file system that you have is one of the features of your operating system. And you can't use the file system from another operating system to implement a new operating system. Most people don't want an operating system that needs to run on top of another operating system. So as a result of that, the C and C++ file types for doing input and output with files might not be available. They might not work correctly within that environment. You might not have certain types of hardware, like a real-time clock. So you might not be able to, the C and C++ functions that exist to get the current real-world time might not exist in your application. You might not have a dynamic memory pool, depending on what sort of memory resources you have available. It might be very difficult for you to use C functions like malloc or C++ facilities like new within reasonable constraints. So all of these things make it kind of difficult to know what is and isn't available when you're writing these types of systems. And this is a problem because even for these kinds of systems, portability is very useful. I mean, for operating systems, it's generally a design requirement. The point of an operating system is often to be portable. For embedded systems, you're having some of the code that you write, even for embedded systems that have very specific hardware components, often a fair chunk of the code that you write could be reused on another platform in the next generation of the product, for example. So having the ability to change targets there can be very useful. Or maybe you don't want to change targets, but you want to change which tool chain you're using because your existing compiler vendor hasn't provided all of the new modern C++ features that you want, and you've found another tool chain that can do something that you think would be very helpful to you. If you have portable code, making that kind of change isn't that bad. But it's not no effort, but it's not that bad. But if your code isn't portable, that could be a real nightmare. If you're talking about libraries, if you are a library implementer, if you can make your library portable to the point where it can be used for these types of platforms as part of implementing an operating system or embedded system, that increases your potential market. So the question is, if we want to make code that is portable to these sorts of environments, what parts of C and C++ can we actually rely on? And so, to that end, the C and C++ standards both define two different kinds of language implementations. There's what's called hosted implementations and what are called freestanding implementations. And the two languages explain the purpose behind hosted and freestanding implementations a little bit differently. The rationale for the C standard says, by defining both conforming hosted and conforming freestanding implementations, the standard recognizes the use of C to write such programs as operating systems and ROM-based applications. Those ROM-based applications are one version of the embedded systems I was talking about before, as well as more conventional hosted applications. The C++ 17 standard says it a little bit differently. They talk about a freestanding implementation is one in which execution may take place without the benefits of an operating system, which it's explaining it in a little bit different language. But the limitations are very similar if you think about these things, because the C version is talking about we want to be able to write an operating system. The C++ version is talking about, well, we don't know what you're writing, but you're writing it in a place where you don't have an operating system available. And one of the versions of that is writing an operating system in the first place. So you wind up in a similar place. So the idea here is that hosted implementations are what we would use for writing conventional desktop and server applications in C and C++. They're what we usually think about when we think about the C and C++ languages. And these implementations have to provide all of the language and library facilities that we might expect for those languages. But there are also freestanding implementations. And these freestanding implementations are what we would use for writing operating systems and embedded systems. And they're only required to provide certain limited language and library facilities. In a sense, freestanding C and C++ are the lowest common denominators for using C and C++. If you want to make your programs portable to the maximum number of C and C++ implementations, the freestanding feature set is what you should be targeting. So what does that feature set look like? So the C11 standard says, a conforming freestanding implementation shall accept any strictly conforming program. A strictly conforming program is a program that uses only features defined in the standard, not extensions that might be specific to one toolchain or another. So, any strictly conforming program in which the use of the features specified in the library is confined to the contents of the following standard headers. And what I want you to look at here is this list of headers. A lot of these exist to provide support for core language features. So we have things in here like float.h and limits.h, which define range information for built-in types like double or int or unsigned long, for example. You have a number of these header files provide alias macros for certain C features. So unlike C++, C did not originally have a Boolean type. So when they went to add Boolean to the C language, they knew that there were already programs out there that had type defs called bool, lowercase b-o-o-l. So what did they do? They called the type underscore capital B Boolean, and then they provided the header file standard bool, which provides aliases for bool, true, and false, the way that we would typically write them in C++. So there are several header files that do things like that. We have ISO 646, which provides international keyboard support, depending on what region you live in. Some of the operators that we typically think of using in C and C++ programming are difficult to write with those sorts of keyboards, so this lets you spell certain operators as with short text strings like XOR. And then there are a few others like studarg, which provides support for writing functions that take a variable number of arguments like printf, and standarddef.h, which provides a lot of common definitions that we're used to using in C and C++ programming, types like size t and common constants like null. So this is the sort of stuff that is guaranteed to be there in freestanding C. So most of it is core language support. There's not a lot of what we typically think of as the library of C available here. So for example, we don't have studio.h, we don't have studlib.h, and we don't have string.h. So at least I should say those headers aren't guaranteed to be there. A freestanding implementation is allowed to provide more of the library than it's required to. But in terms of what you can actually count on being there, it's just those headers I just showed you. So you might not have access to the standard input and output functions like fgetC or printf. You might not be able to do memory management with malloc and free. You might not even have certain fairly basic functions like memcopy and strlen, which I think everyone in the room could probably write strlen in a matter of minutes. And yet it's not actually required to be something that the standard library provides in a freestanding implementation. In fact, none of these headers actually define any real functions. Some of them declare things that look a lot like functions, but they're actually function-like macros. You'd find some of those in studalign.h, for example. Or sorry, studarg.h was what I meant to say. But there are no actual functions in these headers. The C++ standard requires a little bit more. It requires most, not quite all, of the same headers that C requires. And it also requires a few more C++ specific headers. So atomic, for supporting atomic types. There is a version of cstudlib that's required in C++. Interestingly, this is a C header file that wasn't required in freestanding C, but freestanding C++ requires it, but it only has to provide these three functions: abort, addExit, and exit. So it just needs to provide these functions that assist with program termination and shutdown. The exception header for providing the standard exception types, as well as some exception helper functions like getCurrentException and terminate. initializer list for allowing you to write code that uses the initializer lists feature, limits, which is the C++ version of limits.h and float.h in C, new for the various forms of new and delete, type traits for performing type-based metaprogramming, and type info for doing runtime type identification using dynamic cast and type ID. So, and again, a lot of these headers exist to support core language features. You might actually have access to more features than that, but they're not guaranteed. And in fact, even if you have a particular header file, you're not guaranteed to have the full contents of that header file that you might normally expect, as shown by the example of cstdlib. The freestanding version of that header file might only provide these 3 functions. In addition, there are a few other restrictions that freestanding implementations might impose. The biggest and most obvious one is the library limitations, but there are also a few others. So multi-threading might not be available. Both C and C++ are now thread-aware, but they both have this text in the standards that says, under a freestanding implementation, it is implementation defined whether a program can have more than one thread of execution. So it might be available, it might not. It's up to your specific toolchain vendor whether they want to provide multi-threading support within a freestanding implementation. Program startup and termination might look a little different. Most of us are used to writing C and C++ programs where when the entry point of the entire program is a function called main, and the program runs as long as you're somewhere within the body of main, and as soon as you return from main, the program shuts down. But that's not necessarily the case in a freestanding environment. The function that's the entry point for your program is allowed to be called something different in a freestanding implementation. Now, that's subject to certain limitations. In C++, for example, constructors for global objects still need to be run at startup, and the destructors still need to run at shutdown. This is similar to those functions abort, at exit, and exit. Those things still have to have a behavior that's consistent with how the standard describes them. But the scaffolding around that might be a little bit different in a freestanding implementation. Now, other than that, though, most of the language features, the core language features that make up C and C++, are available in freestanding implementations. And this includes some features that some people might find surprising. So floating point arithmetic is required. The types double, float, and long double are all built into the language. So if you are operating on a platform that doesn't have floating point hardware, your implementation has to provide some sort of floating point emulation capability in software to allow you to use these types. You have to have a dynamic memory pool in C++. New and delete are considered to be core language features in C++. This is as opposed to freestanding C, where malloc was one of the things that wasn't necessarily guaranteed. In C++, new and delete are considered to be important enough that you have to provide them in a freestanding implementation. Exception handling, you need to be able to throw and catch exceptions even in a freestanding environment. And you need to be able to perform runtime type identification using dynamic cast and type ID. All of these things are things that the standard guarantees will be available in a freestanding implementation of C++. Now, a lot of operating systems and embedded systems prefer to avoid a lot of the features that I was just talking about. Exception handling and runtime type identification in particular can introduce a fair degree of overhead into the program even if you don't actually use those features very much. So this is a case where freestanding C++ provides more features than a lot of people who use freestanding C++ actually want. And in fact, it's not uncommon for people to use flags like GCC's fNoExceptions to turn off some of those behaviors, to disable exception handling on their platform or disable RTTI. But it's worth noting that if you're using those flags, at that point, you've put your compiler into a mode where it's technically no longer compliant with the standard. You're not really programming in C or C++ anymore at that point. You're programming in something that looks a lot like C++, but isn't technically C++, according to the standard. So, not to say that a lot of people don't do that, just that it's in sort of a strange gray area with respect to the standard. Now, at the same time, there are certain parts of certain language features for which the library support isn't actually guaranteed to be there. So, standard move and standard forward are defined in the header file utility. Now, these are an important part of implementing move semantics and R-value references. If you want to be able to move an object rather than copying it, you would typically call std_move. But utility isn't one of the required headers in freestanding C++. So it's one that's commonly provided on a lot of platforms, but it's not strictly required. You can't be sure that it will be there. So if you want to write C and C++ code that's going to be portable to the maximum number of systems, you want to be aware of both what library facilities are guaranteed to be available on various platforms, which is not very much, as you've seen. Most of the library support that is guaranteed to be there is really the stuff required to support core language features. And some of those core language features are things that you might want to steer away from because a lot of freestanding users prefer not to use exception handling or runtime type identification or some of the other features that I mentioned. So you want to know how to restrict yourself to both the library facilities that are actually guaranteed to be there and the core language features that your users are going to find palatable. Now, as I mentioned, many of the compilers actually provide more of the standard library than freestanding actually requires, even in a freestanding implementation. And unfortunately, there aren't a lot of tools that help you do checking to make sure that you're only using the parts of the standard library that are actually guaranteed to be there in freestanding implementations. So it's kind of easy to accidentally stray outside of that box of the things that are guaranteed to be available in a freestanding environment. And so you have to sort of know what that list of things is and be ready to police yourself in terms of making sure that you don't accidentally use features of C and C++ that aren't guaranteed to be available in a freestanding implementation and inadvertently make your code less portable than you'd intended it to be. So we'll talk a little bit more down the road about some techniques that you can use to protect yourself against that. But another thing I want to mention is, so there are several compilers that provide a -f freestanding flag or some variation of that kind of flag. This is present on GCC, for example. Now, GCC in general provides a full hosted implementation of C++. So if you were going to provide a hosted implementation of C++ anyway, if you're going to provide all those features, what does that flag actually do? What's the point of putting it into freestanding mode? It turns out that modern compilers often have a certain amount of built-in knowledge about what the standard library does. They don't just take the standard library as this nebulous, unknown thing. They actually have a certain amount of knowledge about what the standard library is. And they can use that knowledge to generate more optimized code in certain situations. So here, if I write this code where I create a size t n and initialize it with the value of strlen of a fixed size string hello here, if I run this through GCC, the compiler doesn't actually generate a call to strlen. It doesn't need to, because GCC has the built-in knowledge of what strlen does, and it can see that that string is of a fixed length. And so it just compiles the code as if what I had written was size tn equals 5. It never generates a call to the library function. Now, it can only do that in certain cases. If I'm working in a situation where the length of the string is unknown, where I get the string that I'm going to take the strlen of as a parameter to a function, for example, in this case, GCC will generate a call to strlen because it can't see what the length of the string is going to be in all cases there. So there it has to fall back to the library function. So it turns out that the -f_freestanding flag, what it does is turn a lot of this built-in knowledge that the compiler has off. So the description of the flag in GCC says that GCC does not make assumptions about the meanings of function names from the standard library, with exceptions noted below. And in this case, they're noted on the next slide. So I'll get to those. But why is this important? Well, suppose that I'm working with a version of the standard library that doesn't actually provide strlen. But I'm working with GCC. If this built-in knowledge is turned on, then I could have calls to strlen in some places, like this, that actually appear to work because GCC never generated a call to the function. It just figured out what it was supposed to do at compile time. And then in other places, it would actually try and generate a call to the function. And in those places, my compilation would fail. And I'd get some error message that says, strlen doesn't exist. And I'd say, but wait a minute. That guy over there called strlen just fine. What the heck happened? And it can be a very confusing situation for people. So by turning off this built-in knowledge, you can make sure that all of your calls to strlen will fail. You won't accidentally step outside the boundaries of what your library provides. And it makes it a little bit easier to avoid going to a place you didn't want to go. The exceptions I mentioned just a moment ago that GCC requires are the functions memcopy, memmove, memset, and memcompare. These functions are assumed to be there in GCC, even in freestanding mode. None of them are actually required of freestanding C according to the standard, but GCC itself requires them. The knowledge about how these functions work and what they do is embedded to a certain degree in the compiler. And so the compiler itself expects to generate code that will depend on these functions. So in a rare case, you may need to write these functions yourself, even though freestanding C says they might not be available. Most platforms, they will provide implementations of these functions. But in a rare situation, you might have to provide them to make GCC work. Over time, the -f_freestanding flag has also found another use, which is I'm not necessarily really targeting freestanding environments when I write my code, but what I want to do is I want to substitute a different implementation of the standard library for the one that my compiler would normally provide. So I don't want fewer standard library capabilities, but I want the standard library capabilities that I get to be compiled using somewhat different algorithms and maybe have different performance characteristics. Now, if the compiler is making assumptions about what standard library functions do, there's a risk, a small risk, but a risk, that those assumptions wouldn't hold true for whatever standard library distribution I'm substituting in place of the one that would come with my compiler. So using the -f freestanding flag has become a way in some projects to help substitute another version of the standard library in place of the one that you would normally have with your compiler. Now, this is a little complicated because the dividing line between the core language and the standard library is kind of blurry. We've already talked about there are parts of the standard library that exist to provide language support, to provide library support for language features. But there are also parts of the libraries that really expect a certain amount of support from the compiler itself. So earlier I mentioned the type traits header that's used to perform type-based metaprogramming. This is one of the header files that actually is required in freestanding C++. And one of the things that you can do using the contents of this header file is you can ask questions about types at compile time. So I can write a type trait like isIntegral and feed it a type t. And the member : value of isIntegral t will be true if t is some integral type like int, and false if it's a floating point type like double, or some non-numeric type entirely like a widget or something like that. I can ask the question isAbstract, and in that case isAbstract of t : value is true if the class type that I give it in there is an abstract base class. I can ask isVolatile t : value, and that will be true if t is a type that includes a volatile qualifier. So some of these type traits can be implemented in standard C++. IsVolatile is the kind of thing that you could write using standard template deduction rules without any actual compiler support to make it work. But some of them, like isAbstract, really require a certain amount of assistance from the compiler to actually be able to answer the question of whether or not something is an abstract base class type. It's very difficult using standard C++ to ascertain whether something is an abstract base class while still being able to actually compile your program. So these sorts of interactions can make it a little bit tricky to substitute one standard library distribution in place of another. So it's something that it's worth being aware of if that's something that you intend to do. So freestanding C and C++ is essentially the baseline that you can target if you want to make your C and C++ programs as portable as possible. If you want to be able to use them on the maximum number of tool chains and target the maximum number of systems, freestanding C and C++ is the way to go. But using them can be kind of difficult because you don't get very much of the standard library. You have to make sure that you restrict yourself to only using those parts of the standard library, because if you stray outside of them accidentally, you could make your code less portable. And you also want to stick to using only certain core language features, because freestanding environments often take a dim view of some features like exception handling and runtime type identification. Now, there is work being done on the standards committee to try and make this stuff a little bit easier to use by making some of those core language features optional and increasing the guaranteed portions of the standard library. So there's a paper, Leaving No Room for a Lower Level Language, by myself and another person named Ben Craig, which proposes to make certain language and library features optional in freestanding implementations of C++. So the default implementations of new and delete, exception handling, abort, at, exit, and exit, floating point arithmetic, multi-threading and lock-based atomics, runtime type identification, and thread-safe static initialization. This last one is when you create local static objects in modern C++, there's guaranteed to be a certain amount of thread synchronization built in to ensure that they're not inadvertently initialized more than once. So this list of features should look familiar. Some of them are the features that we talked about before as being things that many freestanding users tend to avoid. Now, multi-threading is commonly used in embedded systems and operating systems, but the standard library version usually isn't what you want to use in those situations. The standard library version of multi-threading really expects support from an operating system. So obviously, if you're trying to implement an operating system, that's not really going to help you out very much. There are plenty of standard, yes?
Question about the default implementations of new and delete?
Yes.
That means basically you provide them, but it won't link?
So in C++, you are allowed to, and this is true of freestanding and hosted implementations of C++, you are allowed to provide, to replace the standard definitions, the default implementations of new and delete that come from your compiler. And you can replace them in various ways. There's a whole, I could talk for quite a while about that. But yeah, so under this paper, you would still be allowed to provide your own implementations of new and delete. But the default implementations that assume the existence of a standard dynamic memory pool would not be guaranteed to be there. You'd get, if you tried to use them and you didn't provide any implementation, then you'd expect to get something like a link error. So now there are many parts of the standard library that don't use any of these features. So lots of the STL algorithms don't use them. The STL containers obviously use dynamic memory all over the place. Although even there, things like array is an STL container. It doesn't use dynamic memory. So there are a number of different parts of the standard library that could probably be made available to freestanding applications, even if all of those features are optional. In some cases, there are facilities like stdarray, which stdarray does have one member function that can throw an exception, the @member function. But it's perfectly usable without ever calling the @member function. There's also the operator square bracket function, which doesn't do the bounds checking that would cause an exception to be thrown with the function. So Ben Craig has some other papers that are making their way through the standards committee that are aiming to guarantee more of the standard library is available to freestanding applications, which in some cases, like stdarray, would mean that the types that you would get would not necessarily provide the full interface that you would expect from a hosted implementation. Only certain member functions might be available, depending on your implementation. And that's something that often strikes people as a little bit weird, but there is some precedence for it. We've seen in C stdlib that the freestanding implementation might provide only some parts of that header file. And so the same thing could be done with standard library types. Now, so if these papers are adopted, it could make the process of writing freestanding applications significantly easier. But there are some unresolved questions that we need to deal with. So one of the questions we get frequently is, if you guarantee that more of the standard library is going to be available, does that complicate the process of substituting a different standard library implementation for the one that I would normally get from my compiler? And this is something that a fair number of people do, and it's a real concern for them if they might be forced to use the standard library that's packaged with their compiler. It's not clear to me that it needs to be a problem. I think that you could write this in such a way that all it means is whatever standard library distribution you substitute in place of the one that you would get from your compiler has to provide all of these freestanding facilities. But many of these implementations already provide those facilities, so I don't think that we're increasing the effort required all that much. But it is something of a concern. There's also the question of C++20 will introduce modules as a language feature. Now, there is not, the standard library itself hasn't really been reorganized into modules. There will be a small, you will be able to treat the standard library headers as if they were modules in C++20, according to the current working draft. But it's not actually reorganizing those header files into modules the way that you might expect. But there is interest in doing that at some point, in making some sort of restructuring of the standard library. And that could be a significant complicating factor in terms of how freestanding applications use the standard library, because if you get a module and parts of it are guaranteed to be there in freestanding and parts are not, that could be a very strange world that we occupy. So that's another outstanding question at this point. In the meantime, what sorts of things can you do to make it easier for yourselves to write freestanding code? It depends a little bit on what sort of application you're working on. So if you're an application developer, if you're writing an embedded system or an operating system, you often have a certain amount of knowledge about where your code is likely to be deployed. This is particularly true for embedded developers. Not always, but in many cases, you'll have some idea of what sort of platforms you intend to target. And that knowledge can help inform your choice of which language features you want to use in your application. So if you have access to floating point hardware, then the cost of using floating point types in your code goes down substantially, because the first double that you use doesn't introduce a bunch of additional library code for emulating floating point operations. It's taken care of in the hardware. So at that point, you might not be concerned about using floating point values the way that I was talking about earlier. And you can make these sorts of intelligent decisions based on what you know about the platforms that you're targeting. So there are many parts of the C and C++ standard libraries that can be implemented in standard C and C++. Not quite all of it, but most of it. So for example, here is a simple implementation of memcopy. Not that big, sort of thing that you could write fairly easily. And you can even do this for functions like std_move. You might think that std_move would be some sort of special function that had a certain amount of built-in logic created by the compiler. But in fact, it can be written in standard C++. It's sort of a complicated definition if you're not familiar with the type traits and some of these other facilities, but it can be done. And both of these definitions were things I found from just a simple internet search. So in many cases, you can find implementations of standard library facilities that might not be available to you just by using the Google or whatever you happen to choose. Now, I realize that's not very comforting, because the point of having a standard library in general is I don't want to have to write these things. I wanted it to be provided by my toolchain automatically. If I have to write all of this code, that's just a bunch of extra stuff I need to maintain. Well, sort of, but I'm not really suggesting that you do this. What I'm suggesting is the fact that you can do it opens the door to making use of more of the standard library than is actually guaranteed by freestanding toolchains. So, because most toolchains provide more of the standard library than they're actually required to provide, you can do things like this, where you use things like using declarations to wrap parts of the standard library that aren't guaranteed in freestanding applications up in your own namespace. And then I can proceed to write my code so here I have a namespace ben, and it just borrows the definition of memcopy from the standard library. And then I write the rest of my code using ben : memcopy. And now, if I ever run across a platform that doesn't provide me with an implementation of memcopy, now I have the freedom to come in here and replace this using declaration with my own implementation of memcopy if I need to. But in many cases, I'll never need to. In a lot of situations, every platform that I try to use will, as an application developer again, situation's a little different for library developers, and we'll talk about that. But as an application developer, I may very well never run across a platform that doesn't provide me with a memcopy. And so I can just get away with doing this, and I never need to provide my own implementation. Now, suppose that I have to target several different platforms, and each one of my toolchains provides a different slice of the standard library. So some portions of the standard library are available on platform 1, and other parts are available on platform 2, and so forth. One of the things that you can use to make managing these, your use of the standard library like this a little bit easier is to use a facility called inline namespaces. So they look like this. So inside my namespace ben here, I create a bunch of additional namespaces. So a namespace for platform 1, a namespace for platform 2, so forth and so on for however many platforms I need to support. And within each namespace, I select the pieces of the standard library, in the case of platform 1, or select my own implementation of things like memcopy for platform 2 as needed. And then I compile one of those conditionally as an inline namespace. And when I use an inline namespace, all of the members of the inner namespace become members of the enclosing namespace implicitly. So even though this using declaration is inside of platform 1 there, if platform 1 is compiled as an inline namespace, I can use it as if it were a member of namespace ben directly. So whichever platform I happen to be using, I just supply the appropriate pound define, and then I select the parts of the standard library that I need and provide the other implementations that I need as appropriate for a specific platform, and it all just works. And having this all in one file like this makes it a lot easier to keep track of making modifications to all of these namespaces at the same time. If I suddenly find a new part of the standard library that I want to use, having this all in one file makes it easy to just go and add them to each namespace and see that I didn't miss any of them. Whereas if they were distributed across several different files and conditionally compiled in, it might be a while before I noticed that I'd forgotten to include a version of memcopy for platform 17, for example. So, as a library developer, your problem is a little bit more complicated because you don't know what platforms you're going to target. Your library could conceivably be used on pretty much any platform. And as a result, you really need to be careful to restrict yourself to only using the features that are guaranteed to be available in freestanding environments. Because even if you knew for a fact that every toolchain out there, every freestanding implementation currently provided an implementation of memcopy, the standard still allows for the possibility that there isn't one, that there's one that doesn't provide an implementation of memcopy, and someone could write a new compiler tomorrow that doesn't provide a memcopy. And you still want your library to be able to work on that platform, even though that platform didn't even exist at the time that you created your library. So in that situation, you really need to restrict yourself specifically to the freestanding feature set. So you want to be careful to document the features that your library uses so that freestanding application users can make an informed decision about whether they want to use your library based on knowing whether or not it makes use of exception handling or floating point arithmetic or things like that. And as a library developer, you really need to, the same trick that I showed you before with inline namespaces really isn't available to you because you don't know which platforms you'll be used on or which tool chains you'll ultimately be compiled with. So if there are any parts of the standard library that you actually need, like std_move, as part of writing a library that's intended for freestanding users, the safest thing for you to do is write it yourself, using the approach that I showed you a little while ago.
Can you use feature identifiers?
The feature test macros, yes. I mean, yes, you could write your library to use the feature test macros to test these things, and that would give you a clearer error message at compile time if they try to use your library on a platform that it wasn't intended to work on.
No, I meant like if std_move is available, then I can use the platform one, and otherwise use my own.
Yes, yeah, you could do that. You could do something like conditionally compile your code so that you use either the library version of std_move or your own version of it. But if you're going to provide your own version anyway, I'm not sure how much that buys you. It might be, might buy you something. The standard library version would probably be more efficient, or at least as efficient as the one you'd write yourself. But yes.
No efficiency concerned by standard move because it's a cast only, so there's no code actually generated.
I was. Thank you. I was really making more of a general statement about the behavior of standard library functions. In general, they're going to be written to a very high quality standard. And it's difficult to assume that you can beat the standard library implementation. Not impossible, but in general, you're not just going to sit down and beat however and write out something that's going to be better than what was provided by your library. So that brings me to the end. We sort of already transitioned into the Q&A section, so if there are any more questions, I'm happy to take them.
I have
Yeah.
one question. A lot of the demarcation is based on headers, and sometimes it seems like a very artificial decision. I mean,
So
you have headers which exclude some of the functions inside their header. It's like, doesn't seem like the right way to separate between these two concepts.
well, so the only header that in the standard actually says that it's going to be you might get a partial implementation of it is cstdlib. All of the others, they don't have this text in them that suggests that you might get a partial version of the header. But it does open the door to the possibility that you might be faced with partial versions of certain header files. I don't know of very many people that do that, but it is a possibility that the standard allows. In terms of is it an artificial distinction whether to sort of divide this along header file lines? I would say yes and no, because in some cases it was retrofitted onto an existing set of header files. The early header files that C and C++ had, they had to make sure that they didn't want to completely change how these things were laid out, so then they had to sort of sort them into freestanding and not freestanding. Whereas with others, I think that they were making a decision about how to group things into libraries, in part informed by the idea that some of these things might be used in freestanding implementations and others might not. Yeah?
Well, it seems to me, though, that what you were suggesting is in your paper, though, stood array is going to be supported.
Yeah.
And that one you said was going to be a partial implementation because it would leave out the act member function.
Yeah. Well, just to be clear, I am not a co-author on that paper. That is Ben Craig's paper. But yes, in that paper, in that situation, one of the things that he is proposing in that paper is that we would create a sort of distinction. The contents of the header files would be marked in a certain way so that certain pieces were identified as the freestanding pieces and other pieces were not guaranteed to be there in a freestanding implementation. And so that would, one of the complicating factors there is that you can't really cleanly divide it along header file lines. And so there is a question of, what do you do in that situation? And the general tack that he's taken in his paper is it's better to provide some of the functionality. If there's a core set of functionality that you can provide for something like stood array, where most of the behavior doesn't rely on exceptions, there's this one function that does, then you get that available to you. He hasn't made the effort to, that I know of, to delve into providing things like stood vector or stood dec, where the usage of dynamic memory is built into the or at least those things, there the usage of memory is governed by allocators and things like that. It's a much more complicated process to separate out which pieces might and might not throw exceptions or raise some of the other concerns that freestanding users have.
And it would seem to me that a similar thing would apply with the header new, although you're not going to, the intent is not to provide the required dynamic memory allocation functions, you would still do placement.
Yes. I don't think that there's well, new is already one of the guaranteed freestanding headers. And so you always get placement new. That's guaranteed to be available today. But
But I thought you wanted to put the other functions on the chopping block.
well, yes, yes. I simplified the description down a little bit for the sake of making it fit on a slide here. Yes, only some of the implementations of new and delete would become optional in that under that paper. Others that don't allocate memory, like placement new, would still be available. Okay, I'm happy to stick around and answer any other questions, but otherwise, thank you for coming. I hope you found it useful. And best of luck to you in all your coding endeavors.